So we'll consider a variation on the spring mass problem from before, or an extension of the spring mass problem from before. This is that compounding idea. So suppose that we have the following system. We have a spring, a mass, a spring, a mass. This will be mass M1, M2, and then another spring connected to another wall right here. So we'll assume that initially we'll say this is at equilibrium. So when this is at equilibrium, we can find equilibrium point and measure from the equilibrium point for each one of these masses. And we'll also assume that the springs have spring constants K1, K2, and K3. So we'll assume 3 linear, that's called Hookean springs, 2 masses, and no friction. And what I want to do is describe to you how to go through and get the equations of motion for this system. This is x1 of t, the position of x1 away, or the displacement of x1 of t away from equilibrium. And this is x2 of t, the position of mass 2 away from its equilibrium point. So we have 2 separate approaches that we can apply here. We actually have multiple. You can go through and do Newton's laws to get the equations of motion. But I think the easiest way of going through and doing this is with the Lagrangian approach, or the Hamiltonian approach now. We now know 2 approaches. So let's go through and first define the kinetic energy of the system. This is just going to be equal to 1/2 the mass of mass 1 times the velocity of mass 1 squared plus 1/2 times mass 2 times the velocity of mass 2 squared. The potential energy of the system is what's called a spring potential, which even for nonlinear spring force relationships, we can often find potentials that generate those nonlinear force relationships. The potential for a linear spring, though, is going to be K1 x1 squared over 2. This is for this spring right here. Now, the potential energy for spring 2 here is going to be a little bit more complicated, because spring 2, the deflection of this spring, depends both on the value of x1 and on the value of x2. Right? The difference between these two between these two values, x1 and x2, right, is going to tell you whether or not this spring is compressed or it's being stretched. So this is factored in here by saying that the spring potential for spring 2 is going to be K2 over 2 times x2 minus x1 squared. Because this x2 minus x1 is the deflection of the spring 2. And then we also have to lastly add in the potential energy of spring 3, which is K3 over 2 times x2 squared. Because x2 is related to the deflection or compression of the spring 2, or spring 3 here. So the Lagrangian approach is to go through, and our generalized coordinates are x1 and x2. Those fully describe our system, so we have to calculate dl dx1. And remember, this is the x1 derivative of k minus u, which is just going to be negative k1 times x1, and then the x1 derivative of negative u here is going to be positive k2 times x2 minus x1. And likewise, dl dx2 is going to be equal to the x2 derivative of the Lagrangian, which is k minus u. Which is going to be equal to negative k2 times x2 minus x1 plus, or minus, because of the minus u here, k3 times x2. And then dl dx1 dot is going to be m times x1 dot dl dx2 dot is going to be m times x2 dot. In the Lagrangian equation of motion, our the time derivative of dl dx1 dot is equal to dl dx1. So we have to have this computed dl dx1 and we also computed this. Because dl dx1 dot is just m times x1 dot. And likewise, when we go through and apply this for x2 dot, we get a very similar result. This will be negative k2 times x2 minus x1 minus k3 x2. And what's really neat about this is that, right, this is there's something called the Euler-Lagrange equations of motion. But for this example, this is a system of two second order, and with the linear springs, linear ODEs. Right, and if you think about it, this is just both of these equations, and I'll kind of just copy them down here. You can really clearly see this. They're just the expression of Newton's second law for the springs themselves. This right here is saying that the rate of change of the momentum of spring 1 is equal to the force on mass 1, or the rate of change of momentum of mass 1 is equal to the force on mass 1 of spring 1 plus the force on mass 1 from spring 2, and the rate of change of momentum for mass 2 is going to be the force on mass 2 of spring 2, which is going to be equal and opposite the force on x1 from spring 2 plus the force on x2 from spring 3. Right, so Lagrangian equations of motion directly recover Newton's second law, but it's recovers it in a way that is very, very quick to go through and get the results for. Sometimes it's not so quick when you go through and directly apply Newton's law. So let's see what this looks like from a Hamiltonian perspective. And the first thing you want to note is that the rate of change of the Hamiltonian with respect to time, which is equal to negative the rate of change of the Lagrangian with respect to time, explicitly this is equal to 0. And the idea here is, well, we first calculate our generalized momenta, and we've already done that. Our generalized momenta are this derivative, this is P1, and this generalized momenta is P2. So we can re-express the Lagrangian in terms of P1 and P2 if we want to. This is P1 squared over 2 times M1 plus P2 squared over 2 times M2. And so the Hamiltonian is negative the Lagrangian plus the summation y equals 1 to 2 of the ith generalized momenta times the ith generalized velocity. So our h function is going to be negative p1 squared over 2m1 plus p2 squared over 2m2 minus the potential energy plus p1 times x1 dot plus p2 times x2 dot. But we note that p1 times x1 dot is the same thing as p1 squared over m1 using the relationship for the generalized momenta. And this is true for both of the generalized momenta in this example. So this entire thing then simplifies to p1 squared over 2 times m1 plus p2 squared over 2 times m2 plus this entire expression right here, which you'll notice is just the total energy in the system. Because this is the kinetic energy, and this is the potential energy of the system. So the Hamiltonian is related to the total energy in the system, and we'll see how to deal with situations where we have friction a little bit later on, where the total energy is changing. When the Lagrangian and the Hamiltonian are not changing explicitly with respect to time, we have a very nice situation here where the Hamiltonian function for a mechanical system is just the total energy in the system. This is when dl dt or dh dt is equal to 0. So the Hamilton's equations of motion then are that q dot x1 dot is equal to dh dp1, which is just p1 over m1 x2 dot, which is our second generalized coordinate of the system, is equal to dh dp2, which is p2 over m2, p1 dot is equal to negative dh dx1, which is negative k1 x1 plus k2 times x2 minus x1, and p3, or p2 dot, which is negative dh dx2. And this is equal to negative k2 times x2 minus x1 minus k3 x2. And so, whereas in Lagrangian mechanics we get a second order, or system of second order linear ODEs. In this case, for this example, two of them, so we have two generalized coordinates. In this example, we get a single system of four first order ODEs. Xi is the vector x1, x2, p1, p2. So this is saying that xi dot is this left-hand side right here. And it's equal to this right-hand side, which is a function of xi itself. Specifically, g of xi is the function p1 over m1, p2 over m2, then negative k1 x1 plus k2 times x2 minus x1, and it's negative k2 times x2 minus x1 minus k3 x2. So the motion of the system is described by an autonomous, or the motion of these two springs is described by an autonomous system of four first order ordinary differential equations. And we can go through and use our previous definition of critical points to determine what the critical points of the system are going to be, and how they're going to be related to one another. But the phase space for the system is a four-dimensional space. And in general, that's the case. This is a very, very general idea, right? We can actually make a definition of, this is done in dynamical systems, to define such a system as a Hamiltonian system. So a system of first order ordinary differential equations is said to be a Hamiltonian system if it can be expressed as the vector of unknown function xi, which is a function of t, is equal to x1 to xn, y1 to yn, and xi prime, which remember is the same thing in block expression as x and y, where x is a vector of n values and y is a vector of n values. Right? Xi is in 2n dimensional space, which we saw before. The phase space of a given system like this has 2 times the number of variables in this first vector x. But I'll just go through and write out each one of these values just for the sake of completeness. So this is x1 dot all the way down to xn dot. This is then y1 dot all the way down to yn dot. So if the system, we have a function called the Hamiltonian, where x1 dot is the partial derivative of h with respect to p1, all the way down to xn dot, where xn dot is the partial derivative of h with respect to pn, and y1 dot is negative the partial derivative of h with respect to x1. Let me move this up a little bit so these are in line. All the way down to yn dot, which is negative the partial derivative of h with respect to xn. Oh, and I just realized I used pn's up here because I was thinking in terms of the mechanics, but this is going to be y1 to yn. And this is directly mappable to what we just talked about. The fact that this is a Hamiltonian system of mechanics, but this idea now is going to be defined for any dynamical system that has this form. We call it a Hamiltonian system, where the right-hand side here, in general, is dh dy, dh dx, or just g of xi. Where h is a function that has Rn to R which has continuous first order partial derivatives. So this is what we define a Hamiltonian system. It comes, as we've seen, directly from an idea in mechanics, but now any system with this property we can call a Hamiltonian system. Oops, and there should be a negative sign right here. So this is a very, very neat idea and can be very, very, very useful. In general, is very useful